In the last video, we were talking about standard deviation in relation to its own mean and kind of viewing it as a number line. And we'll put the little hash marks in there, although I realize that they're not perfectly even. But as we were looking at this, we were discussing how the center point of a distribution is the mean, right? The balance point of any distribution is your mean, which we know would give us a z-score of 0 when we calculated that out. And then we work our standard deviations going up. So we have like 1 standard deviation, 2 standard deviations, 3 standard deviations, and in this one we're going to put, let's say we put 4 here, just for fun. And then on the other side of the mean, we would have -1 standard deviation, minus 2 standard deviations, minus 3 standard deviations, minus 4 standard deviations. And we discussed how whether it's positive or negative is just going to tell us which side of the mean that z-score is on. And we also discussed how we could just kind of look at the raw score and know what our mean is and our standard deviation, and we could pretty much tell if it's above or below. We want to know very specifically where above and below. Well, that's what the z-score will tell us, exactly where on that continuum it falls. And this right to left sort of view of a standard deviation is very useful. However, there is another way to view this, because there's the curve above the number line, which is also of concern to us. You probably recognize that as the normal distribution or the bell curve, and that's exactly what it is. Now, this is a shape that is found naturally in nature. So let's say, for example, I take an 80-pound bag of sugar, and I stand up and I pour it directly in front of me onto the floor. And I don't rock back and forth, I don't wiggle or move, I just pour it straight down. By the time the bag is empty, the mound of sugar on the floor will probably resemble the curve that we're looking at. Most of it will be in that center, and then the amount of sugar will drastically drop off the further we get from that center point. That's kind of what we're dealing with here. The central tendencies tell us how data clusters. And at any given point, data is going to cluster around its mean. And if we were to continue the divisions of these standard deviations through the curve, we can then see that, with 1 standard deviation above or below the mean is where most of any population is going to fall. And any population can be broken down into a normal distribution. Then when we do that, what we have is from one end of the spectrum, so let's say from here all the way down to the other end, you have 100% of any population is underneath the normal distribution. And the mean, which is the 0 point, well, that divides the population in half. So from the mean, if we were to divide it in half, you would have 50% above the mean and 50% of a population below the mean. So the curve is symmetrical. So that division holds true. Under a normal distribution, you have the entire population, 100%, or if we put it in numerical values, 1.00. Half of any population is above the mean, half of any population is below the mean. This division breaks down to what we call the empirical rule. And the empirical rule shows us how the breakdowns continue with the standard deviations. So let's say we're going to say, I'm going to change the color here. Let's go with, let's try this darker red. We're looking at from the mean to 1 standard deviation above. That's 34% of any population. Now that holds true on the other side of the curve as well, right? Because what happens on one side of the curve happens on the other side of the curve, because each side is symmetrical. So you have from the mean to 1 standard deviation below, you also have 34%. Which, just by looking at it and doing the math, you can see that from 1 standard deviation below to 1 standard deviation above, That's 68% of any population. 50% above, 50% below. But more than 2/3 of any population is going to fall right in here. Most of us in any given area are going to fall within one standard deviation of the curve, of the mean. 34% between the mean and one standard deviation above, 34% from the mean to one standard deviation below. More than 2/3 of us are within one standard deviation of a mean. And that should make sense because the mean is the balance point of a distribution, and it's a central tendency which tells us how data clusters. And the standard deviations help us see what scores are going to fall where and what proportion of a population or percentage of a population is going to be within each spot. So let's take a look at another point. Let's say we were going to have from one standard deviation, change the color again, just to make things interesting. Let's change the color to a dark. Let's go to a dark green. What about from one standard deviation to the second standard deviation? And again, that happens on both sides of the curve. One standard deviation below to two standard deviations below. Well, that's a smaller space. There's not as much space under the curve for that. So that percentage should be smaller. And indeed it is. That's 13.6% of any population is going to be from the first to the second standard deviations. So we got our 13 down here as well, 13.6%. Now I'm estimating these. Right? It's more specific in that table that you can download. I put the PDF up, or the your textbook. If you're looking at the portions of Z under the normal distribution, you'll see that this is a little bit estimated. And with estimations, we do lose precision. But for the sake of understanding this and seeing how this breaks down, we're going to stick with the estimations. So what that really gives us then is from the mean to two standard deviations above that mean would give us 47.6%. 47.6% of any population is from the mean to the second standard deviation. So again, that goes for below as well. So you have another 47.6% of a population is going to fall from the mean to the second standard deviation below. That gives us 95.4% from the second standard deviation up below to the second standard deviation above. 95.4%. So over 95% of any population is going to fall from the second standard deviation below to the second standard deviation above. The whole graph is only 100%, right? Because you can't have more than 100% of something. 95% is between two standard deviations of the mean on either side. 47.6 above, 47.6 below, for a total of 95.4% from the second standard deviation below to the second above. So within two standard deviations of the mean is over 95% of a population. That's a lot of us. 68% of us are between the first standard deviations on either side of the mean. And as you could guess, just by looking at the curve and the area under the curve, these percentages are going to get smaller the further away from the mean we go. Because, well, like with the sugar that we poured, not as much sugar lands that far away from the center point. How much sugar? Well, we now know that 68% of it is right there in the center. But let's say we were going to go, and we're going to change the color again. Let's say we're going to go from the second standard deviation to the third standard deviation. And we'll do that below the mean as well. What are the percentages out there? Well, at this point, that's 2.15%. So 2.15% is between the second and third standard deviations. Less than 3% of any population is between the second and third standard deviation on either side of the mean. So if we were talking about IQ, less than 3% of the population is going to be between the second and third standard deviation. That's not very many of us at all, is it? And if we were going to go from, let's say, the mean, let's say we're going to go from the mean to the third standard deviation. Now we're talking 49.8%. 49.8% is from the mean to the third standard deviation. And again, that will hold true over here as well. 49.8%. That is actually an 8. Let's try to draw that a little bit better. So 49.8% of any population is between the mean and the third standard deviation, be that above or below. And if you're keeping up, that puts us at 99.6% from the third standard deviation below all the way up to the third standard deviation above. We're talking 99.6% on that line. So 99.6% of a population falls from the third standard deviation below to the third standard deviation above. The whole graph, again, is only 100%. And this is why in most cases, when people start talking about standard deviations, they don't bother going much beyond 3 standard deviations above or below a mean. Because as you see, that's 99.6% of any population. And that's an estimated. When you look at your z-table, you'll see that we'll go with the proportions or percentages, we go 4 decimal places as opposed to just 1 or 2. But again, like I said, for the sake of this video, we're only going to go this little bit, and it's an approximation. We're not rounding it up to 100%. That we don't do. And to demonstrate partially why, the curve does continue. And despite the fact that 99.6% are going to be within 3 standard deviations of either side of the mean, well, we still could, let me just change the ink color again. I probably should have done that while I was talking before, but, whatever. I'm going to use red. You still could have people who are going to be within the 3rd and 4th standard deviation. So you could still have folks out here. Now, granted, it's going to be a very small percentage of the population. Specifically, between the 3rd and 4th standard deviation, you have 0.12% of any population out there. So less than 1% of any population is between the 3rd and 4th standard deviation. That's not a lot. So when we're talking about IQ, and we're looking at people who are saying they have genius level IQs and all, realizing that if they're telling the truth, if their z-score for their IQ falls between the 3rd and 4th standard deviation above, not very many are out there. Less than 1% is out in that range. And if they're talking about a z-score higher than that, upwards of 4, well, at that point, you're dealing with 0.003% in this area here. And I'll put it out here on the low end too. 0.003%. Very few are out there. Is it possible? Yes, it is possible. Which is also partly why when we're talking about curves in some of the classes, they'll tell you that, you don't want the tails of the curve, which is what these are called out here, the tails. You don't want those touching the axis, right? So you have this space in here because although the numbers get drastically smaller the further from the mean we go, we have to be open to the idea that there could very well be, although it's not likely, there could very well be folks out in that range. So again, although underneath the normal distribution, it is 100%. The breakdowns show you that the further you get from the mean, which again shows us, the bounce point and essential tendency, how data clusters, the less likely it is you're going to find anything way out there. Okay, so now let's take a look at this in what the application really looks like on this. So again, we've already drawn out the curve. I cleaned it up a little bit so we have a fresh one that we can start off with. Now let's say we're talking about, we want to compare some folks. Now, let's say we're talking about IQ. So let's put IQ here. IQ, which again we know has a mean, population mean, equaling 100, right? So that would actually come down here at the 0 point, the mean being 100. And we also know that the standard deviation of IQ is 15. So that being the case, we know that each one of these values is going to be 15 if it's on the upside of the mean, or the north side, or the positive side. And let's just illustrate that here. This is the positive side of things. And over here, below the mean, would be the negative side. And again, it's not qualitative. It's simply directional. It's letting us know what side of the mean are we talking about, or what side of the mean are we on. So, again, if we're talking about IQ with 100, so if we're going one standard deviation up, going an IQ score of 115, 2 standard deviations, 130, 3 standard deviations up, 145. And now we don't usually talk about 4 standard deviations up with IQ because it's so low probability. But we're going to do that right now. So again, if we're doing an IQ of 4 standard deviations up, we're talking an IQ of 160. That's very high. As you know from looking at the slide before, or if you go back in the video and take a look, you'll see how few folks are actually going to be in the range of even 145 to 160. Now let's go to the low end of things. Let's go below the mean. So we have a standard deviation of 1 below. So standard deviation of 15, that gives us an IQ of 85. We go 2 below. That gives us an IQ of 70. 3 below, 55. And 4 below is an IQ of 40. And again, when we're talking 3 standard to 4 standard deviations out, that's not that much of a population out there, as you now know from looking at what came first in the video, or the video before. So let's make some application out of this. Let's say we have a person, we'll say person A, and they have, their raw score for IQ was 115. We would then know that their z-score, if you calculate the formula for z-score, the z-score would equal 1. So that puts them right 1 standard deviation above. We could now take a look at the graph and the way that the proportions break up, and we now know what percentage of the population falls between their z-score here and the mean. Well, we now know that's 34% of the population would be there. We also now know what percentage of the population scores the same as them or greater. How would we do that? Well, we would take the 34% that we know is in here. Right? We know this is 34%. So 34% is in this range here. And we also know that the mean, above the mean, is 50% of a population. So you would simply subtract out 34 from 50, which would give us 16% of the population is in this direction. So we now know that 16% of the population scored equal to or greater than person A here. Now, if we're looking at below, well, we know 34% of the population falls from their z-score of a 1 to the mean. But if we want to know all the way down to this end, I apologize for the lack of a straight line there, we'd have this 34% that we would have to add to, again, below the mean is 50%. So we would have to add 34% to the 50%. And that ends up being 84%. So I'm going to change the color just to illustrate it a little clearer. Let's make it a dark green. So we now know that from their X right here, their raw score, or Z-score, their raw score of 115, which is one standard deviation above the mean, from here to the mean gives us 34%. And then from here down, that additional 50 puts us at 84%, which really means this person scored equal to or better than 84% of the population. This might be more familiar to you as a percentile ranking. When you're looking at how a person scored in relation to everyone else, who did they do better than, equal to or better than, that's the percentile ranking. So if you have a person who has an IQ of 115, they're in the 84th percentile. Now let's take a look at it from the other side. I'm going to change the color again. Oops. Let's change the color. Let's make it a darker purple looking blue. Now let's say we have another person. This is person B. Person B, and their raw score for IQ was a 70. Now we know their Z-score is going to equal a -2. We know that it's going to be negative just by looking at this score because we know it's below the mean. So then we know it has to be a negative. We also know the standard deviation being 15. And we've just plugged the numbers into the Z formula, which we used last week. We'll get a Z of -2. That puts their marking on the graph right here. That puts them here. Now, if we wanted to know their percentile ranking, we're still looking at what percentage of the population did this individual score equal to or better than. So we're still looking from -2 down to here. So one of the ways, an easier way, just by looking at it the way we're doing it now, before we consult the Z table, is we do know that if we were looking at the space from 2 to the mean, well, we already know that that's going to be 47.7%. So then we could subtract 47.7 from 50, which would tell us that you have 2.3% scored equal. They scored equal to or better than 2.3% of the population. So they're really in the second percentile. So that's a relatively low score. Now let's say we wanted to know, well, we have person A and person B, and well, what percentage of the population falls between these two? So we want to know, since person B is here and person A is here, and we want to know what the space is between these two. What percentage of the population falls between these 2 points, between the score that person A has and the score that person B has? Well, we know that from one standard deviation, or a Z-score of 1, to the mean, so that from here to here, we know that that's 34%. That part we know. We also know that from a Z-score of -2, so from here to the mean, we know that that space, or that percentage, or that proportion, is 47.7%. So the next step would be to add those together. And that would tell us that 81.7%, where's my, lost it, oh, there it is, 81.7% fall between person A and person B. Now that's keeping it as simple as possible and making sure in these examples that our Z-scores fall directly on the standard deviations, which makes it a little easier to look at the empirical rule of the normal distribution and say, okay, well, we know that this is 34% to here. We know that's 47.7% to the mean. And being that those are both coming towards the mean, because, we're looking for that space in here, Well, we know that that's going to be 81.7. However, these things don't always have such nice and easy z-scores. So let's say, for example, we have person Y and person Z. And we take a look at the IQ for them. And the raw score for person Y, let's say their IQ measured at, let's say 111. Well, we know that's going to be somewhere in this range in here, right? Now let's say for person Z, let's say that they scored a 90. Well, we know that's below the mean, because the mean is 100, but it's not going to be much below the mean, is it? In fact, looking at the standard deviation over here, 15, we're only 10 points below the mean, so we're not even a full standard deviation below. And when we calculate those z-scores, the z-scores are not going to be as even as the others were. So let's say we run through that calculation. As you guys remember, the calculation is going to be the raw score minus the mean divided by standard deviation. So for person Y, oops, it's this over here, their raw score is 111, which gives us a z-score for them of 0.73. And for person Z, their z-score, it's below the mean, right? Because we can take a look at this, we can see it's below the mean, is going to be a negative 0.67. Those don't fall neatly on the standard deviation marks. And if we wanted to know what's the percentage of the folks that fall between those two, then we're going to have to make reference to the z-table. And I'll show you how to use the z-table